Alright, so last thing we gotta look at in this first trig unit is the idea of trigonometric identities. This is brand new for everyone here, and you've probably never seen the word identity used before in math. And really just an identity is an equation that's true for any value of the independent variable. Okay, and the idea behind these trig identities that we're going to be looking at today is that we're going to be given something that is true, and we're going to have to prove that it's true. And we'll talk about how we can do that as we move forward. So some things, some identities that we've actually seen so far that we didn't necessarily call identities, just called them equations, are, for example, the reciprocal identities. So we know that cosecant x equals 1 over sine x. This is true for any value of x you can choose, so this makes it an identity. Secant x equals 1 over cos x, cotan x equals 1 over tan x. Okay, these are ones that we saw earlier on in the unit. Next ones that you've seen a little bit, but maybe haven't worked too much with, are what we call the quotient identities. And this one says that tan x equals sine x over cos x. Now, if you're looking to see where that one comes from, well, you can look at the fact that in a triangle, sine x equals opposite over hypotenuse. Okay, and cos x equals adjacent over hypotenuse. Okay, so let's see what happens if we actually try to divide these. So if I were to decide to do sine x divided by cos x, okay, what I wind up with here is, okay, well, sine x, as we know, is opposite over hypotenuse, okay, and cosine is adjacent over hypotenuse. Okay, so when we divide, so what we have here is two fractions that are being divided. So I'm going to rewrite this division as just in a more horizontal manner, the way we're used to seeing fractions divided in elementary school. So we have opposite over hypotenuse, and this is going to be divided by adjacent over hypotenuse. And you might start seeing some things that you know are going to cancel here, but I'll go through the steps anyways just to make sure we see it. Okay, so when we divide fractions, we know we multiply by the reciprocal. So what we're going to wind up with is, again, opposite over hypotenuse. Okay, but now we're going to be multiplying by the hypotenuse over the adjacent. Okay, so what happens here when we multiply them together is that these hypotenuses cancel, and you're left with opposite over adjacent, which is the whole definition for tan. Okay, so that's a proof of why that quotient identity works. Okay, we're going to be using that a lot when we work with trig identities. So tan x equals sine x over cosine x, and using the reciprocal of that, cotan x will be equal to cos x over sine x. Okay, a couple other things to look at here. So some other identities that we're going to be able to use. Remember drawing an angle in a quadrant here with a terminal arm at r, and these ratios between these sine, cosine, and tan ratios exist between x, y, and r. So sine theta is y over r, cos theta is x over r, and tan theta is just y over x, opposite over adjacent. Now, the relationship that exists between x, y, and r, well, they're related by the Pythagorean theorem, so x squared plus y squared equals r squared. Okay, so what I'm going to do here, I'm going to take this equation and I'm just going to divide everything here by r squared. Okay, for reasons that hopefully will become clear in a little while. So I'm going to divide everything here by r squared. And let's see what's going to happen here. So if I have r squared over r squared on this side of the equation, well, that's just equal to 1. Okay, so I have 1 over here. Now, x squared over r, so I'm going to have x squared over r squared plus y squared over r squared. Okay, and I'm just going to rewrite x squared over r squared as x over r all squared. Okay, so basically, since both the numerator and denominator are squared, I can take the entire fraction and write that as being squared instead. I'm going to do the same thing over here. This is going to be y over r all squared. Okay, well, okay, why am I doing this? Well, going back up here, x over r is equal to cosine theta. Y over r is equal to sine theta. So if I make that replacement in there, instead of x over r, I have cos squared theta. And instead of y over r, I have sine squared theta. So I wind up with the fact that cos squared theta plus sine squared theta equals 1. and this is now a true identity, something that is true for any angle you choose. And this is called the Pythagorean identity. I'm normally write it as sine squared theta plus cos squared theta equals 1, but again, since it's addition, the order doesn't matter. Okay, and you can try that for any angle you want. In fact, if you want to try it now, let's pick an angle, let's say, I don't know, 42 degrees. Try it in your calculator. Try doing sine squared of 42 degrees, okay, plus cos squared of 42 degrees, and see what that's equal to. It should be equal to 1, but you can prove that in your calculator. Now, one thing with notation here, just to confirm, when I write something like sine squared theta, this is the exact same thing as the entire ratio sine theta, all squared. Okay, it's the same notation used for different things. We usually write it the way on the left so to avoid having to write extra brackets, but these two mean the exact same thing. If, however, it was written so that only the angle was square, like something like this, that would be something completely different. So this is not the same as these, but these two are often used interchangeably. Usually you'll see this one. Okay, but what it means is that the entire ratio is squared, not the angle is squared. Okay, so using the Pythagorean identity, and that's going to be a big identity that we're going to use in trig identities when we're trying to prove them. We can also just do some quick solving here to express them as in terms of just sine squared or just cos squared theta. So let's say I take sine squared theta plus cos squared theta equals 1, and I subtract cos squared theta from each side of the equation. Okay, so I'll be left with just sine squared theta on this side and 1 minus cos squared on the other side. So this becomes a true identity again. That's just equal to sine squared. We do the same thing for cos squared by bringing sine squared over and get 1 minus sine squared theta. So just two different other ways of expressing that Pythagorean identity in a way that might be useful to us. If we want to, we can extend this even further to generate expressions for the reciprocal functions. So let's just say, for example, now this isn't required. I'm not going to expect you to memorize these, but if you're looking at these ones down here, let's say I took, again, sine squared theta plus cos squared theta equals 1. And let's say I divide everything here by sine squared theta. So there, and there. Okay, well, sine squared divided by sine squared is 1. Cos squared divided by sine squared is cos over sine. That's cotan, so that's going to be cotan squared. Okay, and 1 over sine squared is cosecant squared. Okay, so just by dividing everything in the Pythagorean identity by sine squared, I've now generated another equation for cosecant squared, and that's this one right here. If I repeat this exact same process but divide everything by cosine squared instead of sine squared, I wind up coming up with this equation right here. Now, me personally, I never use these two formulas, so again, I do not expect you to memorize them at all. However, if you'd like to have them in your memory bank to use potentially when you're solving a trig identity, feel free to use it, but I don't expect you guys to memorize these. There's always ways around using reciprocal identities when we're actually doing this proving, and we'll work with those. But again, if you want to use them, feel free to, but it's not required. You are, however, expected to have memorized the Pythagorean identity, sine squared plus cos squared equals 1, as well as the reciprocal and quotient identities. You are going to need to have those in your memory bank in order to be able to solve trig identities. Okay. If you're looking for another way of proving the Pythagorean identity, this is just another way that you could come across it. If you remember that sine theta is y over r and cos theta is x over r, well, for the one on the left here, if we multiply both sides of the equation by r, we get y equals r sine theta. Similarly, for cosine theta equals x over r, if we multiply both sides of the equation by r, we get r cos theta. So if I take the x squared plus y squared equals r squared that I had from my diagram on the previous page and replace the x with r cos theta and replace the y with r sine theta, I wind up with r cos theta squared plus r sine theta squared equals r squared. And you can sort of start following the algebra here. So I apply the squared to both the r and the cos, so I get r squared cos squared plus r squared sine squared theta equals r squared. The r squared then gets factored out here as a common factor. So I get r squared times cos squared plus sine squared equals r squared. The r squareds divide out on either side, so you get cos squared plus sine squared equals 1. Just another way of coming up with that formula right there. Okay. Now, putting everything together, these are all the different identities that we have at our disposal. Okay, so we have cosecant and secant. You could also use cotan being 1 over tan, but traditionally with tan we're going to use sine over cos, and cotan will be cos over sine, and I'll explain why in an upcoming slide. And this being the big one here, the Pythagorean identity, which can be rearranged to solve for sine squared or for cos squared. These two down here for secant and cosecant are optional. Okay, now when we're working with trig identities, if something is not an identity, all it will take is one example to show that it's not true. Because an identity is in theory true for every possible value of x or theta, whatever variable you have. If you can just choose any variable to sub in there that makes it not true, it's no longer an identity. If you were to somehow graph these, an equation would be an identity if the left side and right side of the equations produce the same graphs. For the kind of things you'll be proving, if you want to do the graphs, you'll probably use a program like Desmos because the graphs are very, very complicated. The big thing that we're going to be looking at here is this one down here. If it's an identity, then the left side and right side of the equation can be simplified independently, the key being independently, so that we get the exact same expression on either side. And that's what we're going to be looking at today, doing the math and proving that both the left side and right side of an equation are identical and doing it independently. Okay, so some strategies that we're going to look at. Generally, when you get an identity, we want to express everything in terms of sine and cosine. Okay, usually if we get tan, we write it as sine over cos. If we get cosecant or secant, we write it in terms of its reciprocal. When I was talking on the last page about working with each side independently, this means we cannot assume they're equal. We're trying to prove they're equal, so we can't assume they're equal by doing so. So we cannot move things across the equal sign in order to do this. We have to work with each side completely independently. Okay. Simplify as much as you can. That means you might be adding or subtracting fractions, which means finding a common denominator. And whenever you can, look for opportunities to factor. Okay. And again, all this probably seems strange because we haven't actually seen an example yet, but hopefully it'll make sense once we look at one together. So here, for example, is an identity. Okay, so I'm trying to prove, for example, that cos x times tan x equals sine x. Now, looking at the graph here, over here I have cos x, tan x, and sine x on the same grid. They're producing the exact same graph, so we know it is an identity. However, we're trying to actually prove this algebraically. So let's just get this out of the way. Okay, so if we want to prove this algebraically, now one of the things I mentioned is that we have to work with each side independently to prove they're equal to each other. So that means I'm going to start out by rewriting the left side of the equation. Over here, I'm going to have cos x times tan x. Okay, and separately I'm going to have the right side of the equation. You have to keep these sides separately because you can't move things across the equal sign by adding or subtracting or multiplying, dividing from either side. And number one, this ensures that this won't happen. Number two, it's part of the process for formal proof. Okay, so you need to keep the left side and right side completely separate. So the right side, it just says sine x. There's really not much I can do to simplify it. For the left side, I'm going to try and do some algebra here, or do some substitutions here that will make me transform the left side into looking like the right side. So all I can really do here, I see I have tan x, and tan x I know from one of my quotient identities is equal to sine x over cos x. Okay, so what I'm going to do is I'm going to replace tan x with sine x over cos x. So I'm going to have my cos x here. Okay, and again, tan x is replaced with sine x over cos x. Okay, and what's going to happen now is you'll see I have cos x here and cos x here. These are going to cancel, so it's just going to be equal to sine x. So at this point now, the left side of my equation is now equal to the right side of my equation. So since these are now equal to each other, I say that this is now equal to the right side, and I am finished. Okay, so I've made both sides of the identity equal to each other. I have now proven it, so I'm done. Okay, so that's the general idea. We're going to start off with two different expressions on either side of the identity, and we have to manipulate the two sides independently to get them to equal to each other. Okay, so that's one example. There's another one here that you can try and take a quick look at, and we're going to continue this in part 2 of the lesson.